we should express this as an integral, and we know how to do it. We should choose very small disk around that node of radius epsilon. And we know by Cauchy formula, since the function is holomorphic there, that f of z node is expressible as the integral over this little circle here. Of f of z, z minus z naught is n. Okay, now let's take a look at the following picture. I'm erasing the boundaries of the annulus because I don't need it. So I'll just keep the information I'll need. So there's a bigger circle of radius r2. There's a smaller circle of radius r1. And there's a little circle around that node of radius epsilon. So I add more cuts like this, and now let's see let's take a look at the following counter of integration, the following path. So it goes like this, like this, like this. Notice that the direction of we go around the point A for this disk and for this disk is the same. So it's in my case it's clockwise. Clockwise here. I continue, and then I continue here, and it becomes counterclockwise. So it goes around, it goes around, it goes around. So then I return here, and I return here to this. So I start here, and then I complete this. This circle. So if say this is my base point, then or maybe this is my base point. It doesn't matter because it's a closed path. So we see that this this counter is constructible because I mean I can start moving this here and this here, and in the end it will contract. So so if we say denote by f of z z minus z node, then and again denote the whole thing by gamma. The integral over gamma of f of z is 0 because the path is contractible, but also it equals, let's count. So let's say that this is L1, this is L2. Then I'll have two of these, and then another one with different sign. So it will be integral over dk ar1 f dz. It's the only, no, it's so another one with the same sign. Integral dk z naught epsilon f dz minus, since the direction changed, integral over dk ar2 f dz, and then the canceling ones. So I'll write plus integral over L1 minus integral over L1 plus integral over L2 minus integral over L2. So we can ignore this part, but we see that this plus this minus this equals 0. So let me rewrite this. So this calculation shows, so we get the integral, so f of z naught, which is 1 over 2 pi I integral over dk z naught epsilon f of z minus z naught dz. So it's this one is this minus this. So it's 1 over 2 pi I integral dk a r2. I wonder if I'm making this sign right. I think so, but let me check. Yeah. F of z minus z naught dz minus 1 over 2 pi I integral over dk a r1 f of z minus z naught dz. Yeah, and remember that our goal is to obtain Laurent series expansion for this at the point K, and now it's clear the method what we'll use. So remark. So denote this by 1 and this by 2. Yeah. So 1 will provide terms of Laurent series with positive exponents of z minus a to the k, and 2 will provide terms of Laurent series with negative. Okay, so this is the plan, but now let's realize it. And exactly like we did in this Cauchy formula for derivatives, so the first one. So on dk a r2. So of course we start rewriting 1 over z minus z naught, and this is 1 over z minus a times 1 minus z naught minus a z minus a. So notice that by my choice, absolute value of z naught minus a, so this is a distance from z naught to a, is less than the denominator. So I can expand this in this. So I'll get 1 over z minus z naught becomes 1 over z minus a sum at n equals 0 to infinity, z naught minus a, z minus a to the n. So then f of z, z minus z1 is sum n equals 0 to infinity, f of z, z minus z1 times z naught minus a to the n. So then when we start integrating, so I think I should keep it a little bit lower. So So then the summand we are looking at, so it's 1 to pi I integral dk a r2 of f of z to z minus z naught z becomes 1 over 2 pi I integral dk a r2. So same thing, f of z, and then sum f of z is z minus a to n plus 1 dz. No, dz at this point is at the end. Z naught minus a to the n. And then we'll change the order of integration, of summation and integration. So as usual, and then we'll do fine, because what we get is, this will also go inside. So now this becomes coefficient. Good. So this indeed looks like the Taylor series part of this Laurent series expansion. So these are our expected coefficients, and if you think about it, it's exactly the one we wanted. Now let's do the second one. So this, we had two summands. So this is the first summand. Now the second summand. The second summand comes from integration on this second curve, second circle. So here the inequalities will be different. So 1 over z minus z naught, we will expand it differently. So yeah, just remember that absolute value of z minus a, z naught minus a, is r1 over absolute value z naught minus a, and this is again less than 1, so we're allowed to expand. Let's expand. So one over a minus z naught stays, then sum n equals 0 to infinity z minus a to the n z naught minus a. And now, because of this, we have different sign, which actually is good. Equals minus sum n equals 0 to infinity z minus a to the n z naught minus a to n plus 1. Very good. So then thus f of z minus z naught becomes minus sum f of z z naught minus a n plus 1 z minus a to n. So then integrating. Again, we expand as a sum and then change the order. So this will become minus sum, n equals 0 to infinity. And then 1 over 2 pi integral f of z times z minus a to the n and then outside we get z naught minus a to the power minus n minus 1. So so if we think about it, what's written here, I mean dz. I just want to keep both summaries on the blackboard. So just look at this formula and the formula above. So we get that f of z naught, which was this integral over this little epsilon disk, is a difference of 2, 1 minus 2. And notice that 2 comes with a sign minus, and there's another minus here, so they cancel out. So then this becomes what you have on top. Plus what we have here. And here I'd like to change the summation so that this would be my parameter. Then it will become sum from so n equals minus infinity to minus 1 and then 1 over 2 pi r integral over dk a r1. So we're almost done. F of z, z minus a to n plus 1 dz. And again, z naught minus a to the n. So now the only difference from the formula we really want is the following, that here we're integrating over R2 circle and here we're integrating over R1 circle. But recall that we already, so we already know that this integral over dk a r of f of z, z minus a to any power does not depend on r. It is the same for any r between r1. So this means that we can replace this integration by integration of the same kind. So I'll just continue writing. And this is plus the sum of negative parts. But the integration now is over the same circle of radius R2. So in total, it's the expression we wanted. We obtained the Laurent power series extension for f of z naught. Good. So it was quite a complicated computation, but apart from standard steps, everything is absolutely straightforward. So let me make a remark which is important. So see, this correspondence works like this. So functions Laurent series. So given Laurent series, you produce an annulus of convergence. So, I mean, O and a function. In the other direction, given a function, well, holomorphic function, and this annulus, so together. So this remark is that we really need both the function and the annulus where we decompose it. We produce Laurent series. Yes, Laurent series. So, which means that for the same function in different annuli, you'll get different series. So I included this as part of the data because keeping the same f but changing the annulus will produce different series. I want to demonstrate this. There's a big example in the book, which will be the last thing to talk about today. So big example, demonstrating exactly this feature that the area where we're doing it is important. So let's take a function which is very, very simple. So f of z, which is just, it's a rational function. So it's holomorphic outside points 1 and 2, of course. Now, it's a good excuse to start drawing. So we have the point 0, which is taken for no reason. But so there's a point 1, and there's a point 2. So you can choose different disks or unmovie. So possible disks are like this. So I drew it in a way so that it would not collide with the other ones, but so possible choices of where we produce series is, say, disk around 0 of radius 1. I shifted it a bit so that it would differ from other ones. Also, we could take an annulus around 0, but here. So this would be A around 0 between 1 and 2. I could take this area. This would be A 0 to infinity. What else could I do? I can take the center at the point 1, and so see, if we take the center at the point 1, of course we need to throw away the point 1, but also the next singular point is 2, so we can take we can take k prime 1 of radius 1, and this is the same as A1 0 2 or 1 0 1. So it's an annulus around 1 with inner radius 0 and outer radius 1. So it's this punched disk around 1. Also, you can take k prime around 2. So 2 is also a singular point. So the next singular point is 1. So the radius convergence will be 1. So it will be k prime 2 1, which is A 2 0 1. And let's expand our function in each of these. So expand f of z into series in each domain. So the function doesn't have singularity at 0, so predictably in k 0 1 I'll just 1 minus z minus 1 half 1 over 1 minus z over 2. So this becomes nice series in z. So predictably, there's no polar part because there's no singularity at 0. No negative thing. So let's try a 0 1 2. So f is Now, first summand is expanded differently because now the distance from 0 is greater than 1. But it's still less than 2, so we can write it like this. So this becomes predictably so it's actual Laurent series with both negatives and positive parts. Now, in the somehow in the disk around infinity, so outside of the disk of radius 2, so in A0 to infinity. So we should think about this as a disk around infinity in some sense. So then we expand in 1 over z both summands. And this becomes a nice series in 1 over z. So this was not interesting because somehow we centered at a point which was not a singular point. So now let's try this punched disk around 1. So we'll be expanding in z minus 1. So now the polar part is ready because we'll be expanding in z minus 1 and we have already 1 over z minus 1. And then the rest is minus 1 over 1 minus z minus 1. So this of course gives rise to good Taylor series, and this is the polar part. So we'll get minus 1 over z minus 1, like z minus 1 inverse minus sum z minus 1 to the n and greater equal to 0. So we get this summand gives us order 1 pole at z equals to 1, which is predictable because it was a rational function. So the last one I want to talk about in class is same thing around 2. So in this punched disk around 2, so we have the same f of z, and again polar part is ready. And the rest is expanded. So again, because of this summand, we get order 1 O and Z equals 2. So in principle, if you think what I did so far, there are other choices. Of the area of the domain. For example, another series will appear if I take the annulus around the point 1, but with the inner radius equal to 1 and outer radius being equal to infinity. So if you look at the picture, this means that I am outside of the singularity. So the singularity is at 2 and the distance is 1. And when I'm outside, it's another domain. Or I can do a 2, 1 infinity. And again, so I center at the point 2, but then I step away so that the point 1 would be outside of the domain. So there will be more possible series. So all this was to illustrate the principle which was over there on the blackboard, that when we switch between series, expansion, and functions, the area where we do it is important. So this annulus, this choice of annulus is important. So of course, many different annuli give the same answer. So when we say do it, say here, we could. So for example, with this one, we could choose this radius to be smaller, or we could choose this 0 to become epsilon. And then the expansion would stay the same. But as you see, there are jumps when we pass from one type of area to the next. And just informally, jumps happen when we pass, so when the center stays, jumps happen when we pass through singularity. So, good. That's all for today. It was quite an extensive chapter, and I think the most important material is what happened today with this Laurent series expansion. So as I promised, I apologize I didn't finish today, but I will finish by the end of the weekend. It will appear on the web.